Preparing to live stream. Welcome everybody to another. Oh no, this is the wrong stream. Okay. I'm trying to broadcast this on YouTube simultaneously, but it's not. Something is not working correctly at the moment. Okay, I think I was just clicking on the wrong link. I'm being told that it's live already. Okay, we are live on YouTube, people, so watch what you say.
How far are you from Cape Town?
Well, I am in Cape Town myself.
Yes, but university?
Well, the university is about, what, 900 kilometers, 1,000 kilometers?
Oh, okay.
Yeah. Yes.
How often you go there?
In a normal year before COVID, it would be 5-6 times a year.
Mm-hmm.
Last year was 3 times, hopefully more now.
Mm-hmm.
So we'll go again in February. Normally what we do is we take the whole team from Cape Town and we go to the university for a week to kind of unite the two teams for a bit.
Mm-hmm. Yeah, South Africa is really a very big country. 1,000 kilometers, it's a lot.
Yeah, you get a very different sense of businesses here. We were just on a trip to Namibia with some friends, and it's kind of the minimum unit of driving is 100 kilometers.
Yes.
Anything less than 100 kilometers doesn't count.
Yeah, so yes.
And it's and usually it's 100 kilometers on a dirt road.
Dirt road. I thought that there are good, you know, there is Oldfish Bay, which was a very important port for at some moment for South Africa. I don't know, there should be very good roads from Johannesburg or so on to Oldfish
Well, there are, I mean, well, the main highways are quite good, but of course, all the interesting tourist places are in the middle of nowhere.
Yes.
So then you start driving on little roads. But it's a lot of fun, and I mean, it's the scenery is so spectacular that you don't mind having to drive 200 kilometers. I mean, you just see
Alec,
so much.
I feel that South Africa is as Russia is not very punctual. It's already your time 12.
Yeah.
When you will start?
Let's a couple more minutes.
Okay, no problem for me. I know Russian tradition.
Yeah, we always give a couple of minutes for people to filter in.
Okay.
But we can already start the recording. Or we can decide to start when we hit a certain number of participants.
Okay. You are deciding, it's okay.
All right, well, we're 3 minutes in, so let's assume we can start. So welcome everyone and Happy New Year, and welcome to the year's first colloquium. So our speaker today, as we like to say, needs no introduction. In this case, really needs no introduction. But of course, I'm going to have to introduce him anyway. So you all know, well, if there's one thing you know Professor Sunyaev for, it's for being the S in the SZ effect. And this is work he did a long time ago. I think, Rashid, it was right after your PhD, right? It was not your PhD, it was right after.
It was exactly the time when I already had PhD when it was published, but
right.
When I wrote it, I was still a student.
Right. And then, of course, this was about the same time that, to put it in perspective, I think Fanarov and Riley were writing a paper about radio galaxies about the same time. And for myself, I was busy getting born. So yeah, this was a long time ago. And since then, Rashid has gone on to do pretty much anything and everything in astrophysics and cosmology, but I think he has always had a soft spot for the hard end of the electromagnetic spectrum. And of course, to observe at the hard end, you need to go into space. So he has been involved, I believe, in, he has led several Russian space missions. Well, not personally physically led into space, but led in a chief scientist capacity, I believe. And now he is chief scientist at the Institute of Space Science Research in Moscow, and he is also a director of the Max-Planck Institute in Garching. And I believe today he will tell us about the latest Russian space science mission, and a very successful one. So without further ado, Rashid, over to you. Questions are going to go into chat in Zoom, so we can look at them when you finished and answer them. And yes, please go ahead.
Yes, thank you for introduction. It's a pleasure for me to speak for people not only in South Africa, but I heard that there are also people from New Zealand. And these all countries which, when I was a child in Tashkent, now it's Uzbekistan in Central Asia, this was my dream to come sometimes to South Africa and to New Zealand, but it never was possible. Therefore, I am happy at least to give talk for people in South Africa. I will speak about SRG Orbital Observatory, Spectrum Röntgen Gamma Observatory, and it was launched 2.5 years ago, and I will tell you a few words about abilities of this observatory and about some results. Yes, this is before launch. Our observatory in the clean rooms of huge industry, Lagrange space industry near Moscow. It's practically Moscow now, but it's in suburb. And this telescope is already, this observatory is already ready to go to the launch site in Kazakhstan, Baikonur launch site, far to the southeast. And you see the main part of the spacecraft. This is navigator platform, which was produced in Lavachkin and tested. And there are two telescopes. One is Russian telescope, Arctic-C, you see it here, which was produced by our institute, Space Research Institute, and also in the Federal Nuclear Center of Russia in Sarov, where my, how to say, mentor, teacher, Yakov Zeldovich, who spent maybe, yes, more than 10 years of his life developing, Russian atomic bomb, Russian hydrogen bomb, and so on. Fortunately, I was working with him only in astrophysics field. This Arctic-C Russian telescope, 350 kilograms, and we also negotiated with Günther Heisinger, who is now director of science of European Space Agency, but at that time he was director of the Max-Planck Institute for Extraterrestrial Physics. And with Günther, we invited him and his team also to supply a device for our observatory. Günther told us, okay, there is a device with 50 kilogram weight, which is able to see of the few thousand clusters of the sky. And I told him, no, we need device which will see all rich clusters of massive clusters of galaxies in the whole observable universe, so that all massive clusters of galaxies will be observed by this mission. And Günther was very unhappy. He told how it is possible. Finally, he and his team found the way, but device grows enormously. It is 808 kilograms. You see the dimensions 3.5 meter and 1.9 meter diameter. It's really very big device. And you see here real people who are rather tall, and you see how big is the observatory. It was launched, and how we see how artist is thinking it should be observed in the space for some aliens. You see here eROSITA, German telescope, Russian telescope, Arctic Sea, and this is the navigator platform, just spacecraft itself, solar panels, and so on. Whole observatory was integrated, launched, and operated by Lavachkin industry of Roscosmos. But Germany participated with this very good telescope. Other things are from Russia. And it is important, we are very happy. I was working with 4 Russian scientific spacecraft and led by Russia. And I can tell you that we never were working absolutely every day without holidays and so on. Till now, I am very suspicious now. Till now, we are working for 2.5 years, every day without any interruption. And all data are coming to 2 big dishes. One dish is in Ussurisk. It is very close to Pacific coast of Russia, to the boundary with China and with North Korea. It's Ussurisk. Second dish, the 70-meter dish, and 64-meter dish is staying near Moscow in Bear Lakes. It's maybe several tens kilometers from Moscow, from boundaries of Moscow. It's close. And there are also dishes in Baikonur, but they are much smaller. It is Kazakhstan, it's somewhere here. And part of the data from spacecraft, from German device, half of the data are going to Munich, in Germany, to the Garching, in reality, to the institute which created the eROSITA telescope, and everything is going to Moscow, to Space Research Institute, which created Arctic Sea telescope, and which has a right to process half of the data of eROSITA telescope. Yes, this is our orbit. We were launched on July 13, 2019, Proton launcher. You see it, Proton. It's a beautiful launch. And you see we were launched to the L2 point, Lagrangian libration point of the system, Sun-Earth system. It is behind, you see Sun, Earth, and Moon are from one side of spacecraft all time. Now James Webb telescope is also flying to the same point. There is Gaia. There was working the Planck, very successful Planck spacecraft, the Planck cosmological spacecraft. We were flying to this point 100 days. You see, this was 100 days until we went to our hello orbit. And during this flight, there were adjustments, calibrations, and also long observations of interesting areas and sources in the framework of performance verification. Everything went smoothly, and we made already 4 full revolutions around L2. Yes, this is how we are going on our orbit, hello orbit around L2. This is our spacecraft, and it is all time one of that axis of the spacecraft is directed to the Earth and Sun, which are very close. And here there is a side when on opposite side we have a lot of radiators to cool down our detectors. Detectors are working with a temperature -85 Celsius. Yes, this is our cooling system, and spacecraft rotates with period for 4 hours. Therefore, it makes during the day 6 revolutions around the globe, and slowly changing this z-axis, moving to within 1 degree. And field of view of Rosita is 1 degree. Therefore, we are observing during 1 day 1 strip on the sky, going through it 6 times in 1 day. Yes, this I told you, and it's important to say why. People are asking me often why every source on the sky is observed 6 times per day, but only once in a half a year. In half a year, we are making a full revolution around L2. This permits us, these 6 points per day, permit us to look for the short time variability of the sources, which seems very, very important. Yes, this Arctic Sea telescope, it was, how to say, the main ideology came from Mikhail Pavlinsky. Unfortunately, let's say fortunately, he had seen the first data from his telescope and processed them himself, was analyzing them, was happy, but unfortunately he left us in a year after the launch. Now this telescope has the name of Mikhail Pavlinsky Arctic Sea telescope. You see it, 7 coaxial mirror system here, mirror system. These are detectors which are produced by a group of young engineers led with Vasily Levin. And these are mirrors. We have Russian mirrors, but the best mirror during the test, we found that the mirror produced in Marshall Space Flight Center are still better than our mirrors, and they were launched. These are the mirrors. Okay. These are 2 telescopes and their sensitivities, energies for X-ray photons, 0.1 keV, 1 keV, 10 keV, and 100 keV. And this is Rosita, effective surface area of the telescope. And you see it is very good from 300 eV up to 2.3 keV. Then it drops very strongly. And this is a tail. But after 6 keV or 6-7 keV, the second device, which is Arctic Sea, becomes better. Arctic Sea, you see here, it is really good up to 30 keV energies. It's hard X-rays. In comparison, there are with green, you can see the sensitivity curve of the NuSTAR best American spacecraft in hard X-rays. You see that they are not very far each from other. Yes, these are the mirror system of Rosita, and both telescope, Arctic Sea and Rosita, using the grazing incidence optics. And if X-rays are coming to the flat X-ray mirror, they will be at energies of the order of keV fully absorbed. There will be practically no reflection. Vulture in Germany, this Voltaire in reality, in Germany after the Second World War, proposed to the scheme for microscope using two scatterings, on one parabolic mirrors and hyperbolic mirrors. And people immediately recognize that it's possible to use also the same optical scheme practically for telescopes. And now all X-ray observatories which you know, XMM Newton of European Space Agency or Chandra, great telescope Chandra of NASA, and there are many others, they all are using similar system, Vulture 1, where there are many coaxial paraboloids and hyperboloids, and coming X-rays scatter once on parabolic mirror to very small angle of less than 1 degree. Then it's very good reflection. Then they go and scatter on hyperbolic mirror and coming to the focal plane, and it's possible to make image. And this is how the X-ray telescopes are working. And in Rosetta, and practically the same is in Arctic Sea, only scattering angle is smaller. In Rosetta and in Arctic Sea, we have 7 separate coaxial mirror systems. Each of them consists of 54 paraboloids and 54 hyperboloids. You see this there here. Yes, and then surface, then focal plane, and in focal plane we have, we have 7 independent CCD, X-ray CCDs. And pixel size is very small, CCDs are rather big, and field of view is 1 degree in diameter. Angular resolution of the system for point sources is 25 arc seconds. We have possibility to localize every source with 5 arc seconds, and we know the axis of the spacecraft any moment with precision of the order of 1 arc second. And this is very good, and spacecraft is working and pointing us in excellent way. Stability is very high. It's never was during after the launch, it never was worse than 4 arc seconds. Just stability, how we were observing. In 2007, 2 space agencies, Roscosmos and Airspace Agency of Germany, DLR, they made agreement because it was difficult to understand how to share the data from Rosetta, because from the beginning, Russian side told this telescope should, during 4 years, only observe whole sky to make the best in the world image of the sky in X-rays. And finally, we came to the idea, or agencies, let's say agencies came to the idea that for the data processing and publications of Rosetta results, on 1/2 of the sky will be responsible Russian scientists, and German scientists will be responsible for results from another hemisphere. It's our sky in galactic coordinates. This is the SRG A star, supermassive black hole, North galactic pole, South galactic pole. This is a boundary. Everything on this side, you see here is a well-known source, 3273, South ecliptic pole, LMC, SMC, what you see on your sky every day, and we never in the north. All of them are processed by Max-Planck Institute of Extraterrestrial Physics and German consortium, many universities in Germany. And this site, where is, also well-known objects. These are, for example, Coma cluster of galaxies, Perseus clusters of galaxies, Cygnus loop, Casei, many very well-known X-ray how to say, black holes, let us say, in binary system CIGX1, GRS 1915, SS433, you know, many well-known objects there on the Russian side, and there is also the North Ecliptic Pole. It's okay, now you know. I will speak about results only obtained on this part which Russian scientists are processing. There are beautiful data from this part, but today I have time only to talk about the Russian scientists, the data obtained by Russian scientists. After half a year, we observed whole sky. And as I told you, immediately after half a year, German scientists made the map of this part of the sky, and we made a map of this part of the sky. Then we told, oh, it's pity, we should show something to the community. And then we decided just to, how to say, to add two parts. And they were added after small, how to say, corrections of the position. We constructed this map where no one photon from this site was processed in Russia, no one photon from this were 400 million for X-ray photons, where all these photons were processed in Russia. But map is beautiful, you see it, we see beautiful things, North Polar Spur, you know, a lot of activity here on the south, and this is a Cygnus loop, Cygnus super bubble, many sources here, Perseus cluster of galaxies, Coma cluster of galaxies, Shapley supercluster, Vela supernova, Orion, you know, a lot of Large Magellanic Clouds, you see them here. It is a lot of different things we observed, but most important were these tiny points. Maybe you see a lot of white spots here. These were more than 1 million point X-ray sources which we detected. It's impossible to see here 1 million points, even they are here on this point, on this map, but to see them, it's necessary to make this giant, how to say, map with dimensions of several tens of meters, then it is possible to see 1 million points on this map. But this is beautiful. I will tell you several additional things about it. You can see here, and this was first all-sky map obtained by Rosetta telescope, and it had more than 1 million sources. And you see here Milky Way. You see this is a Milky Way. I will tell you why it is, how to say, blackish here. And traces of huge explosions in the center of our galaxy, which appeared maybe 50 million years ago. And you see characteristic time for them, and they're huge. This is 3-color RGB map, all 400 millions of photons with energies between 300 electron volts and 2,300 electron volts, which were detected during a year of continuous scannings, are presented here. Red color corresponds to photons with energies from 300 TeV to 600 TeV, green from 600 TeV up to 1 keV, and blue to 1 keV, 2.3 keV. You see it. Today, we have 1.8 year of scanning of the whole sky. We have 4 full such similar maps, and altogether we have more than 1.5 billion of X-ray photons. Obviously, map is much more sensitive, but in general, it's very similar. But already here on this map, we had, this was the best map in the world. It was already first our map after half a year of flight was contained almost 8 times more X-ray sources than the former world best map of the German Rosat satellite obtained in 1990. and Joachim Trumper, who was leader of Rosat spacecraft, came to me and told me, Rashid, yes, your map is better, but my map was practically 30 years ago. I congratulated him because it's unbelievable that during 30 years his map was the best in the world. Now our dream is to create X-ray map of the sky, which will be the best during next 20 or 30 years. You see this, and let's go further. Yes, and 3/4 of 1 million objects on this first map, where we ourselves were amused that this is everything goes according to, how to say, our predictions, theoretical predictions. You see that 3/4 of 1 million objects are distant quasars and active galactic nuclei, powered by accretion of matter onto supermassive black holes residing in the centers of the galaxies. You see these small points, they 3/4 of them are the supermassive, accreting supermassive black holes. When I was coming to the astronomy and astrophysics, majority of people were not believing that black holes are existing. Now, the same people like me and of my age, they are living in the universe where majority of X-ray sources are, millions, are supermassive black holes. These objects are far beyond Milky Way at distances of hundreds of millions and billions of light years. But in addition, we see more than 200 galactic stars with active coronae like our sun, but hundreds or 1,000 times more bright in X-rays. We see them, and in addition, we see also already on this map 20,000 extended objects. And these are mainly clusters of galaxies and, rich is wrong my English, and rich groups of galaxies with hot gas, and also supernovae. One of the, I already told you what's about the features above and below plane of the galaxy. But red here, this is the map of American Fermi spacecraft. And Fermi spacecraft is observing gamma rays with energy higher than the 1 GeV, and mass of the proton. And they are distributed in the plane. The particles radiating at such energies, cosmic rays, are distributed along the plane of the galaxy, where the sources are, and in addition, where the magnetic field doesn't permit to leave the plane of the galaxy. And there are Fermi bubbles, you see here. And we are amused that Rosetta bubbles, which we discovered, these are Rosetta bubbles, that they are surrounding the regions with cosmic rays which radiate in gamma rays. It is very interesting pictures of this type, and there are huge bubbles filled by cosmic rays mainly, which are radiated in gamma rays and which were detected by Fermi spacecraft. And these are Rosetta envelope by hot gas with temperature of the order of hundreds, thousands of millions degrees. And we know everything about this gas now, its density, because we see the characteristic lines of ions, and there is a lot of beautiful science. Let's go further. I told you already about Milky Way. This is a plane of Milky Way here. And you see immediately that this Milky Way is absolutely dark. And above, we see very bright regions. These are Rosetta bubbles here on the boundary. And this is Cygni superbubble. You see everything here around. And why it is so dark plane of the galaxy? Because there is a lot of cold gas, neutral and molecular hydrogen dust, and so on. And this gas absorbs soft X-rays, just strong X-ray absorption, and we do not see in the energies from 300 electron volts up to 700 electron volts, there is practically nothing. When I go to the region from 0.7 to 0.3 keV, you see already that this absorption is much weaker. But in addition, here above our galaxy, I practically do not see point sources. They are very small amount. And they are there, but they are much more difficult to observe them, and they're absorbed. And these objects, this radiation here is coming from hot gas above the plane of our galaxy, which is halo or local bubble, boundary of heliosphere, and so on. We are trying to find exactly where is this gas which we see, which is so bright. You see it here. And in the plane, there is enormously strong absorption. Here, we see already these millions of objects, which are extragalactic. There's all this warm emission, continuous emission at small energies, this is galactic emission, or halo of galaxy. And here we see really X-ray background, and we see the millions of supermassive black holes and so on. We are sensitive up to energies 8 keV, but this is a map at 6 keV, up to 6, from 4 to 6 keV. And see here we see only 600 objects. You know, it's much smaller amount of photons, and majority of the sources are from the plane of our galaxy, and these are neutron stars and black holes and white dwarfs in binary systems. And our spacecraft can not only scan the whole sky, but it has possibility to scan restricted objects on the sky up to 150 square degrees. And this is excellent mapping of the sky. Before, all existing spacecraft, they were making many pointings here and then constructing map. It was very difficult. We are making this continuously, and map is very smooth and good. This is a Lockman Hole image of it, which we made during flight to the Lagrange L2 point. And on 20 square degree, we see here 9,000 X-ray sources, 250 extended, 185 are already confirmed clusters of galaxies. And this is our deep survey. And we plan after 2 years to scan many regions of the sky with a lot of details with this deep scanning. Another example of the deep scanning. This is at 25 square degrees, in 20 degrees from galactic center. Galactic center is somewhere here, and you see it. And this is a plane of the, it is, yes, it is above plane of the galaxy, it's rich, galactic rich. But look how rich is what we see here. We see here, for example, T-Tauri star in X-rays. We see star-forming region, which is very variable. These young stars are blinking here. This is supernova remnant. And I told you about color, that red color means that gas radiates at low energies, and yellow is somewhere in between, and green or blue, this is hot gas. And you see here another supernova, more young, because it's blue. Pulsar, we see just ordinary star very close to us, just projection. And there are also thousands of objects, and some of them are extragalactic quasars. And we see a lot of hot gas, and this hot gas fills 90% of the volume of our galaxy in the plane of the galaxy. 90% and only 10% is neutral hydrogen and molecular hydrogen. It's very interesting to see. And you see huge absorption in some regions. These regions are filled with the cold gas, and they're black here. It is, and we have many such maps, and it is beautiful, and there is a lot of science which people were unable to study before. We have excellent spectroscopy. You see here, this is a supernova remnant signal loop. You see giant supernova. This is our field of view, and it is 400 seconds per pixel with just 1 day of observation. You see here, not observation, not pointing, it's during the scan. We are observing this, for example, we are 6 times going here, and every time it is less than 70 seconds. We are going through this region. And with these photons, we see in signal loop for 400 seconds per pixel, we see line hydrogen and helium lines, like lines of oxygen, iron lines, L2 shell, neon, hydrogen, and helium like. This is silicon, this hydrogen like silicon lines. We see a lot. This is, I think, this is sulfur. And we see them. Yes. This is very much more close to you, this supernova 1987A in Large Magellanic Cloud. This is long observation of XMM, and these observations of Rosetta. And Rosetta sees nitrogen-like, hydrogen-like nitrogen. I am speaking hydrogen-like. This is nitrogen nucleus with 7 protons, 7 neutrons, with 7 protons, and only 1 electron left. And then this is copy of the hydrogen atom, and there is line, and we see the Lyman alpha line equivalent to the Lyman alpha line here. It's oxygen. We see both hydrogen-like and helium-like line, neon. You see in neon also hydrogen and helium-like neon. Magnesium, we see again 2 lines, silicon, sulfur, and so on. And you can see that we are, our data, our CCDs and mirrors are working not, let's say, not worse than XMM. This is XMM and this is Rosetta. And people who created spectrometer, PM camera on in Max-Planck Institute for XMM, they created a camera also for us, and they were very happy with their progress, but progress was during 20 years. And this is a spectrum in hard domain for bright source. This is microquasars. All of you know about W50 radio nebula, and the SS433 jets. There are jets with velocity 0.25 c. I will show it in better scale. You see now here, Eldar made the picture. This is a spectrum, and this is a spectrum which we are observing. You see black points, but we know now that there are 2 jets, and 1 jet which is recessing, and with this angle, when we observed it, it was a redshift 0.168, and you see the lines of silicon and sulfur from here, and these are lines of iron and nickel. And this is approaching jet, which has negative redshift. It has not redshift, but how to say, a blue shift. And in blue shift, you see again the same lines of silicon, but blue shift, you see there is difference between these lines and these lines. And these lines obviously are much brighter because this jet is shining towards us. And you see the lines of iron This is helium-like iron, hydrogen-like iron, and this is helium-like neon, hydrogen-like neon. Not neon, excuse me, nickel. This is nickel. Yes, and these are beautiful spectra. We are getting them up to, you see here, oh, excuse me. I cannot say, speak. Yes, let us continue. Yes, we are scanning we are scanning sky, and you see here, this is Cygni. When we were scanning, this is the beginning. First time when we were trying to make the scan of the sky. And this is 1 degree white and very long strip on the sky. This already normal scan around sky, around the globe, and not globe, but 2 point, and around the axis to what globe? Yes, to the Earth. And all scans intersect in vicinity of the north ecliptic pole and southern ecliptic pole. And these are normal scans. And this is one day there was, I think, strong solar flare, and we were unable to observe. And you see it's dark strip on the sky. How we are scanning the sky. And in this region, our sensitivity is huge. And immediately when we saw to it, 2 to 2 degrees, we saw quasar. Just with eye, you see the quasar at redshift 2.7, and this is cluster of galaxies, well-known Abel cluster at redshift 0.8. Very, very bright, and it is extended. This point source, and this is extended source. We immediately see this, and this cluster of galaxies was observed by Planck spacecraft, and due to the Oleg mentioned the Z effect, due to a Z effect as a shadow on the sky. You see, but because this is proportional to, effect is proportional to density, and X-rays are radiated as density square, X-ray image is more compact than a Z image. And we can compare, measure temperature, measure from comparison of these two things, immediately give you density, distance, temperature, and so on. Yes, this exposure map, it's very non-uniform, unfortunately. But I am checked what is the situation with Planck. It is similar, very high exposure in vicinity of southern and northern ecliptic planes, ecliptic poles, and then you see low exposure and high exposure region. This is because when we follow our orbit, we are moving with different velocity. That speed, degrees per day. Average should be 1 degree, but on half of the orbit, due to the conditions that what is the distance between Sun and the Earth, Earth and the axis of the spacecraft, there are restrictions. We cannot keep 1 day. The spacecraft is moving sometimes with velocity of the order of 0.6 degree per day on some parts, and sometimes 1.5 degree per day. Is that this brings us to the strong non-uniformities of exposure. And what gives this exposition map for 4 sky survey from December of 2019 till December 2021. And you see here that half of the sky, the exposure, this is a sky area. You see here, whole sky is 40,000 degrees, and half of the sky is 20. And half of the sky has exposure of the order of 800 seconds now. only 800 seconds, but we have a lot of information. And then it increases, and in vicinity of the poles, we have exposure which is close to 200 seconds. And we don't need so high exposure because due to the confusion noise. As you know, Oleg was telling us about Fanarov time in Cambridge, but at the same time, Peter Scheuer was working there, who told that it is impossible to make the counts of the sources on the sky if you have more than one source on the 40 resolution, field of resolution of the instrument. And here we are in confusion. Okay. What is these are source counts. You see the red one. These are the sources, the extragalactic sources, quasars. And blue one, these are stars. How we choose stars? Stars we choose in the following ways. There is Gaia spacecraft, which has more than 1 billion of stars. And every object which we are observing, we're looking, is it on the Gaia star catalogs? Because stars are moving on the sky. They're in our galaxy, and there is proper motion. And Gaia measuring this proper motion. And extragalactic objects do not have proper motion. Therefore, we immediately separate them, and you see how different log n log s curves. The source counts are from stars, which are mainly, there is already plane geometry. We feel the plane of the plane of the galaxy, and for the extragalactic objects, it's well-known slope. We are very happy, and majority of this, you see, we are observing objects with a flux in X-rays, 10 power minus 10 ergs per centimeter square per second, I think, yes, per second from the point sources. And the weakest objects which we see here are of the order of 3 or 4 times 10 power minus 15. These 5 orders of magnitude in the brightness. And this is for both galactic and extragalactic objects. Yes, I told you already that this is accretion. I have no time to tell you how the matter falls, black holes is eating a lot of mass, and then it can produce the relativistic jets, and this surface is very hot and radiates in X-rays. We are observing these disks everywhere practically, and it is great because there are predictions, and majority of predictions, theoretical predictions, are observed. But this is a map, very old image, which is very old. We prepared the map, this redshift, 0, 1, 2, 3, 4, 5, 6. And this is the X-ray luminosity observed by Rosita, from 10 power 41 ergs per second to 10 power 48 ergs per second. This is 7 orders of magnitude here, and redshift up to redshift 6. And 140 quasars, which we are observing, but for which there are redshifts. And you see this map, and majority of objects which we are observing are around redshift 0.5, somewhere here. You see a lot of them. But we see also objects that we discovered first, our discovered quasar at redshift 6.2. You see it. And it is, this object is the most bright X-ray objects at redshifts higher than 5. We are observing many of them, and question is, what are these most bright objects? I think that many of them should be blazar and so on. There is some beaming because luminosity is enormous. For black hole to produce 10 power 47 ergs per second luminosity, it's necessary to eat several masses of the Earth per second. You understand me how much this black hole should eat to at the Eddington limit to have such luminosity. It's enormous. It should eat many solar masses per year. Okay, and we are discovering enormous amount of these objects, quasars, which nobody before, they are in the photometric surveys, but nobody was interested and there was no spectroscopy. And now Russian telescopes, the biggest Russian telescope, it is 6-meter telescope, but majority of telescopes which we are using are 1.5, 1.6, 2.5 meters. And Alex Vishcherikov organized a group of young people, his students and graduate students, and they're using machine learning and neural network programs, and they are discovering the objects with high redshift. High redshift, we are telling, with redshift above 3 or 4. And these objects immediately with 90% success, they're discovering objects that you see Lyman alpha line, and this is on 1.5 meter telescopes. In Russia, never these telescopes were observing this, for example, Lyman alpha, this nitrogen 5 line, nitrogen line, and there are many other lines, C4 and so on. And you see Lyman alpha line, which is 1216 angstrom. It's coming here, for example, here at practically 6,700 angstrom to us. Therefore, it's very interesting. And I told you already that Pavel Medvedev discovered a quasar at redshift 6.2 using Rosita, and this very interesting objects. VLBA now is trying to detect radio emission from this object. You see the spectrum of the quasar at redshift 5.502, and you see all lines which I mentioned, Lyman alpha, Lyman beta. You see that these lines are all in ultraviolet, but they are coming to us at 7,500 angstrom, 8,500, 9,500 angstrom C4. And it's beautiful to see how they're coming. A lot of quasars, and people on Russian telescopes are very happy, but we have so many objects, especially variable, that now we are using also Western telescopes, biggest. Yes, during the whole sky survey, only during for us, surprise was the comparison of first and second sky survey. Every day during half a year, we are observing one strip, which is 1 degree wide and 360 degrees long. And after half a year, we are observing the same strip. And from the beginning, we thought that we will detect some amount of objects which are variable. Here, during 2 sky surveys, only on our hemisphere, 907,000 sources were detected with probability higher than 6 sigma. And you see here, this is the red is first survey, and blue is second survey. And there is difference for the bright. We immediately see this on the bright. For bright objects here, there is enormous variability of the sky. I will show you next slide. You see here, there was nothing. And after half a year on the same place, we see very bright objects. Here, no one photon, and here hundreds photons from the same point. And this point source we know, and typically we detect 3-5 objects per day, changing their flux more than 10 times during half a year. But we see in addition objects which change 50 times brightness. Just now we are writing paper about magnetar in another galaxy. There are many discoveries. And for example, we detect one good tidal disruption event candidate per 10 days. And immediately when we inform optical astronomers, these candidates are followed by the telescope in Russia and in American, Palomar, Keck, 10-meter Keck, and Zwicky transient facility led by Sri Kulkarni. And you all heard, I hope, about tidal star disruption by a supermassive black hole. It is supermassive black hole, and this is the tidal radius. When star is entering this tidal radius, then, tidal forces are so strong that star is disrupted, and part of its mass is going to infinity, and part is captured, forming accretion disk, and new source appears, which are enormously bright, super Eddington, and this is few months. We have now, I can tell you, 60 good TDE candidates. First catalog of 13 our TDE events discovered by SRG Rosita is published already in monthly notices. And a lot of objects are now observed by many X-ray observatories and ground-based observatories. These are people who are working on it. I do not have time to tell the names, but a lot also of PhD students. We are very happy because people are working very hard. But I wish to tell you about extended objects. There are clusters of galaxies, and you see here Coma cluster of galaxies. And this is group in vicinity of Coma. And there are hundreds of clusters of galaxies around, but they are not only in the Coma supercluster, but also far behind the Coma at cosmological distances. We are very happy to give the statistics for this field. But much more important, what we see here, object is bright, therefore we see here the shocks. This is how now we can say what was the path of this group of the galaxy, which is merging with Coma, cluster of galaxies. It's going so and then returns. And you see, we see primary shock, we see secondary shock, we see contact discontinuity, we see the breach. You know, it's unbelievable. This is hydrodynamics with characteristic time 1 billion years, which we see, and everything is in the lab, and all this in the potential well of the dark matter. It's extremely interesting to see and to have such beautiful data. And I have no time to explain, but when you compare Planck image and X-ray image, you immediately can find what is the temperature of the gas in Coma, and it changes from 2 keV here, from 20 million Kelvin in vicinity of satellite of group of galaxies, and in central part temperature reaches 14-16 keV. And this just 2 Rosita measurement in continuum and Planck shadow on the sky. Immediately you are getting information about distribution of temperature. It's beautiful. And you see, we see thousands of extended objects on the sky. This is center of source, and we know that this point source will be here. And this is a cluster of galaxies. We see the emission around from intracluster gas, and this is some traces of filaments and many other things. And we are observing during first survey on half of the sky, we detected at the level more than 5 sigma, 7,500 unknown clusters of galaxies. During 2 scans, it was already 14,000, and now we have of 30,000 clusters of galaxies on the whole sky. If we go up to 100,000, on the whole sky 100,000, on our side 50,000. This will be practically all objects in the universe, an observable universe. I will not say comparison between Atacama Cosmology telescope in millimeters in the Atacama Desert in Chile, 5-kilometer height, and our observations. This is the same region. We are much more sensitive than Atacama Cosmology telescope at redshifts below 0.8 and comparable at higher redshifts. I can tell you so. Atacama Cosmology telescope sees in our part of the sky 15 in the footprint, which is they observed 1,500, 1,600 clusters of galaxies, and we are observing 5,700 objects. But majority of them are at up to redshift 0.8, but Atacama sees up to 175. This is because as that effect doesn't depend on the redshift. I will show you the supernova remnants which we are discovering. This is very large remnant of the thermonuclear supernova explosion in the halo of our galaxy, 1.3 kiloparsec above plane of the galaxy. And there are no radio, no any traces in radio, in gamma rays, optical or infrared spectral band. And you see beautiful ring here of emission, and practically all emission is going in oxygen lines, and we find them. This is brightness of the halo, and this is brightness of the supernova shock. It's beautiful. This also published, therefore who is interested can look to this paper of Chorazov et al. This is a huge group of people and a lot of students who is looking on diffuse objects like clusters of galaxies, diffuse sources in the galaxy, on solar system, we see comets and X-rays, and so on. But I will show, this is the last part of my talk, I will show you the image in X-rays of Pleiades. It is, I don't know, is it visible or not on the southern sky, but on the north sky, it's beautiful constellation. This is the stellar cluster, diffuse stellar cluster, and these are 7 sisters, bright stars. We do not see them in X-rays, but we see more than 100 X-ray emitting stars in this region, just from the same region. And it's enormous amount of stars. We see the spectra and so on. And Gaia, many thanks to Gaia, they have 2 filters, and they can immediately find to construct Gershwin-Russell diagram. And according to their data, we also see that majority of our objects are the M stars and FGK supergiants. We see this 10% of all skies are bright in X-rays. I will show you one simple thing. This is the ratio of X-ray flux to bolometric. And in the case of M star, this more than % of energy of stars is going in X-rays. And sun is, you see here, this is the sun, total emission of solar corona. It's here. And we see objects which radiate much more. And we see many 100,000 of stars now, variable flares from them. It's a lot of interesting thing. But for us, very interesting is what is the situation with stars around which people detected exoplanets. What is the radiation environment for these stars? I can tell you that we detected practically several hundred of these nearby stars with exoplanets. We detected X-rays from them. But may I say only one word, that we do not yet see in X-rays a single star with exoplanets in habitable zone. If there is life, then at least they have rather good radiative environment around and not too much cosmic rays and X-rays. Yes, we have excellent timing. You see the timing, pulsars observing. Arctic Sea has resolution 23 microseconds. and you see how blinking pulsar, and there are shocks, and so on. Rosita sees them in excellent way. And final, my two slides is the discovery of LOFAR, the radio telescope in Holland, radio interferometer, 144 megahertz. They detected something strange in the region of NEST 2047 group of galaxies. In reality, they discovered this object and thought that it is in the group of galaxies. And they asked us to look what Rosita, just scanning, sees it. And we discovered there is supermassive black hole. We discovered gas, which is filling whole this volume, and there are both permits to create bubbles. And there is paper from, first author is from the group of Lofar, Brienza, and it's the Nature Astronomy. You can easily see this paper, and I will show you the interpretation. And these are structures which are observed by LOFAR, very strong activity which occurred 1.5 million years ago due to this black hole. And this is now there is a recent activity, and bubbles of cosmic rays are formed, and then they will go up in the X-ray atmosphere, in the hot gas atmosphere, to create new such beautiful structures. I think that this is Mercat can do and discover, I hope, a lot of such objects, and this is different evolution. It's M87 on different time scale. We see it, and you see a lot of young people group on Baikonur side. This is the launcher. You see how small is the launcher in comparison with our young people. And you can, if you are interested, you can look to the review paper, SRG Orbital Observatory telescope, which appeared in December in Astronomy and Astrophysics. And there is a lot of authors, and again, beautiful picture of the launch, and many thanks for your attention.
Thank you very much, Rashid. That was amazing. And some of those results are just absolutely staggering. We do have some time for questions if people are not very hungry. Would people please raise their hands? Yeah, I see some hands already. Rob, yeah, okay, so Rob Fender has a question.
Great, even Rob Fender came to this talk. Excellent.
Hi, Rashid. Fantastic talk.
Yes.
Thank you very much. A lot of those results are actually new to me. I've not been keeping up as much as I should. If you had, so you did a kind of tour de force of all the results from the mission. If you had to pick out what you think is the most exciting or your favorite result, which one would it be?
I think that the favorite result is obviously, I can tell you that in nearby future, we will publish, we are observing different types of the tidal disruption events. Some of them have, how to say, very high power low X-ray spectrum, and there is a activity this, it's not normal accretion disk. And then we see a lot of tens of tidal disruption events with absolutely normal Shakura-Sunyaev disk, with all properties similar in optics. Everything is going according to the theory. But how is going the transition from one to another, we should also understand, and to see is there radio or not. It's also very important. And most beautiful result came several months ago. We see the magnetar in another galaxy, and it's also beautiful. Just we see how its evolution. Rosita detected it on the very early stage. It was absent in 3 hour, how to say, it was absent in 3 hour surveys, and on the 4th surveys, on the place where no one photons was coming, there are thousands of photons. You understand? It's enormous, and we see such objects up to redshift 0.6. I am also amused what is the sensitivity. And with clusters of galaxies, just we are on the half of way to detect 100,000 clusters with, together with Germans on the side of the sky. And I can tell you, again, I repeat, you know what is observable universe, everything within CT, and what within CT theory prediction was that there is no more than 100,000 clusters of galaxies, and it seems that we are close, together with the Z results, we are close to detect all 100,000. And this is for our, you know, everything in observable universe. It's unbelievable, and we can find the redshifts and everything, masses, distribution. We can see how they were born. Because, for example, at high redshift, at a redshift higher than 1.5, there is only 30 or 40 objects like coma, so massive. But we will certainly see them and will report. I think.
Yeah, no, it's fantastic. The tidal disruption events is very interesting. I'd be very interested to, if it turns out that all the ones with the very hard spectra turn out to be the radio loud objects. You know, that's the kind of working hypothesis.
Yes, I know.
Be very interested to see what it turns out. Thank you.
Yes.
Great, thanks. Any more questions? Raise your hands, please. I've got a very general question, actually, first. What would be the first thing you would follow up on with something like Meerkat? All the results you've shown.
Oh, I can tell you that I am afraid, we were discussing after your talk on our December conference. We had discussion in our group, and difficulty is the following, that everybody is proposing to observe his objects on the Meerkat. I told no colleagues, we will choose one or two, ask, is it possible or not? And if first attempt will be absolutely successful, then we can continue. But we have many objects to discuss, and Oleg, within several months, we will come to you with proposal asking how, with whom to contact, and how to propose, how to see objects. You see how beautiful thing is coming with LOFAR, and I can tell you that we are open for another type of collaboration. If Meerkat is observing something interesting on sky, and they are interested, are they X-rays or not? Contact us and we will inform, because we see whole sky. If this is not, but if it is on the German part, ask our German colleagues. If it is on our part of the sky, we will be very glad to inform you what is there in X-rays at that point.
Excellent. Well, I believe we have another open time call coming up soon, so that would be a perfect time to try something.
And when it will be, just so that we will be not late as usual.
Oh, I'm not sure. If Fernando is still on the call, maybe
okay, it will be very good.
Yeah, I'm not sure about the exact timing, but we will keep in touch about that. I also had a technical question, just out of curiosity. So the eROSITA has these the optical system has 7 independent cameras.
Yes.
So is that like 7 fields of view at the same time?
No. It is the same field. They are co-aligned. It is the same field, but to make telescope and stellar and mirror system independent, in reality, these are 7 telescopes which are observing the same region on the sky and scanning the same region on the sky. Therefore, it is just to increase, because our request was very high sensitivity, and this was most economic way to get the effective surface area 2,400 centimeters square. With this very stretched configuration, when you can scatter photons only to half a degree, for example, you understand yourself. It is extremely difficult to get thousands of square centimeters. And we got it. Background is low. We are very, very lucky. Now situation is a little worse, because there are solar flares, and they are increasing enormously our background for short time.
All right. So if you were to try to make one big one, it would just have to be much longer because of the scattering. Okay. I think I understand. All right. Do we have any more questions from the audience? Any more hands? I don't see any more hands. In that case, well, let's thank Rashid again.
Yes, thank you for your attention.
Yeah, thank you very much, Rashid. This has been an amazing colloquium. And yeah, we look forward to seeing what Meerkat can do together.
Okay. Thank you then. Bye.
Great. Thank you very much.
Thanks a lot.
Okay. If something, please write. Okay. Bye.
Yes, we will. Thanks very much. Okay. Bye, Rashid.